Section 8.2 today, and it's operations with matrices. Tomorrow we'll introduce something new, which is inverses, and we'll get a new way to solve systems. So you have like the row echelon and the reduced row echelon form. And then in matrices, you can also use inverse matrices to solve a system. So we're going to come up with a lot of ways to solve systems of equations using matrices by the end of the chapter. But today is just adding, subtracting, and multiplying. And there are two types of multiplication we're going to look at today. Multiplication by a scalar, and then actually multiplying matrices together.
I just have a question.
Yeah.
So, if you have a non-square matrix, matrix in your calculator, doesn't auto just think that's an augmented one?
I mean, yes. Yeah, probably. There is, like, if you see in your matrix menu, there is something for, like, augmented, but I don't ever use that. So, yeah.
I tried using it, but I got syntax error, so that's why.
Oh, I'll look at it and see if I can figure out what the augmented matrix in the calculator actually does. I don't actually know. I never use it. Okay, so first thing we want to talk about is matrix equality. Okay, matrix equality is a very basic idea, which says two matrices are equal as long as their corresponding entries are equal. It just means they're the same matrix. In order to be equal matrices, that would mean you'd have to have the same order, so that you had the same number of entries in each matrix, and then all them entries were the same. Here's an example of two matrices that are equal. Even though the second row is fine. Even though the second row looks a little bit different, we can argue that those matrices are really the same, correct? The square root of 4 is 2, and 1/2 is 0.5. So all of my corresponding entries are equal, therefore the matrices are equal. We can use matrix equality to solve questions like this. Solve for x and y. If you know the answer, don't say it. Some people are going to write this into their notes. Turn to your shoulder buddy or small group and tell each other what x and y are.
X equals y is x.
Okay, there are two ways to solve for x, and when you guys talk to each other, it sounds like we got the right answers. One is to look at, probably the easiest way to solve for x is look at first row, second entries. You have x in the first matrix, and then you have 2 in the second matrix. So x must equal 2. Note that there is another entry that has x in it. It should be the same or confirm what we have already said x is for this particular set of matrices. So you could have also found x by using the first row, first column entry, and saying that x plus 1 equals 3. Well, that also confirms or verifies that x equals 2. So it wouldn't matter which one you use, it should solve the same way. You don't have to solve both. Okay, but now you know x is 2. And then y, you would use second row, first column entries, and so you have 2y equals 6, therefore y equals 3. Okay, so very easy to solve for a variable if you know two matrices are equal. Okay. Next thing we want to talk about are adding and subtracting matrices. So for addition and subtraction, one thing that's really important, they have to be the same order. So rows and columns, again, have to be equal. That must be true for matrices to be equal to each other, and that has to be true for addition and subtraction. When adding and subtracting matrices, you basically just add and subtract corresponding entries. So So that would be like the whole reason why you need to have the same order. If one matrix would have an extra row, you wouldn't have anything to add with it. So then you couldn't add those matrices together. Okay. And the last thing that we'll look at before we do actual matrix multiplication is scalar multiplication. We kind of touched on that already with row echelon form, where we just multiplied a row by a scalar. Well, now we're just saying multiply the whole matrix by the scalar. Okay. So in scalar multiplication for matrices, every entry in the matrix is multiplied by a scalar. That would be a great way to work with a matrix maybe that was full of fractions, right? Multiply by the LCD for all the fractions in the matrix, and then you would cancel out all the denominators and have whole number entries.
Would it be, I'm just gonna, I don't know how to phrase it, but for multiplying matrices, we're not gonna have to FOIL those giant equations, right?
I don't think so. Please write these two matrices in your notebook. Matrix A, first row is 4, 0, negative 3. Second row is negative 1, 8, 4. And also matrix B, 1, 0, negative 1 for the first row. 4, 3, 7 for the second row. And we'll just use these matrices to do a couple of quick things. The first one, very quick, very easy, is going to be a scalar multiplication. We are going to do 2 times matrix A. If I were to show my work, I would write out something like this. 2 times, and then I would actually write out the entries for A. And remember, this is different than the scalar multiplication we use in row echelon form, where we only multiply a single row by a scalar. Now we're multiplying the whole matrix by the scalar. So everything gets multiplied by 2. Pretty simple, yes? Okay, so combining that idea with what we talked about for addition and subtraction, could you please work on A minus 3b for me, please? In your notebook. A minus 3b. I think it would be wise on problem sets, quizzes, tests, that if you're doing something like this with a couple of steps, show some of that work. Only because if you make a small calculation error, I won't be able to figure out what it is if you don't write anything down other than your answer matrix. So what I did was I wrote down matrix A, and then it's pretty easy for me to do scalar multiplication for matrix B, so I just went ahead and wrote out that 2 by 3 matrix where everything was multiplied by 3, and now I'm going to subtract them. Okay, so as long as you subtract every entry, you should be okay. You can change that to adding the opposite, where you would like distribute the negative to all the entries, but I would guess most of us would be okay with remembering subtraction, especially for matrices. So we'll get 1, 0. This is negative 3 minus negative 3, so you should get a 0 there. Double check to make sure you don't have negative 6. -1 minus 12 is -13, 8 minus 9 is -1, and 4 minus 21 is -17. So really the troubling piece of this is going to be making small arithmetic errors. Things like 2 times 3 is 5. False. 3 times 3 is 6. False. Okay, so those are a lot of the things that I see when people are taking quizzes and tests without a calculator. They kind of like rush through those small arithmetic things and then you make a small mistake. But show your work. Okay, so I can see what you did. Any questions there? Okay, let's get into the actual matrix multiplication. This would be like one of my main concerns for people to make sure they have practice and that you really feel very comfortable. And like you can do this on Monday of next week when you're taking a quiz. So you could do it on Friday next week when you're taking your test. And you'll have some questions that ask you to multiply matrices on your problem set. Okay. So in matrix multiplication, here's the rule. They don't have to be the same order anymore. But you do have to have the number of columns in your first matrix equal to the number of rows in your second matrix. And so rows in the first must equal columns in the second. So for example, suppose your first matrix has the dimension or the order m by n. It has m rows and n columns. In order to be able to multiply that with a second matrix, because I have n columns in the first one, my second matrix must be some n by p. Okay. Now, what is p? We don't know. It could be the same as n, or it could be a totally different number. The key there is just that the columns in the second columns in the first match the rows in the second. If that's true, then that also helps you find the order of your product matrix. So if you can multiply matrices together, your product matrix will have a new dimension, whatever m by p is.
So you can only square a matrix if it's a square shape.
I would argue yes. Because you couldn't take a 2 by 3 times another 2 by 3.
Yeah.
Note that this means you could have like an entirely new order for your answer matrix that doesn't match one of the matrices you multiplied. You could do a 1 by 2 times a 2 by 3, and then you end up with a 1 by 3 matrix. So just by the way one looks, you don't know what your answer matrix is going to be until you think about it. I think that's really helpful to me when I'm organizing my matrix multiplication. I always figure out what my product order is first. Okay, so here are two products that we're going to see. Like, can we multiply these? Two matrices. Can we multiply these two matrices together? If we can multiply the two matrices together, what is their product? So A is the square matrix 2, -3, -2, 5, and I'm reading the rows there. B is my same matrix from before, 1, 0, -1, 4, 3, 7. If I were asked to multiply these matrices, I would check orders first. You don't want to multiply things that can't be multiplied. Okay, that's kind of pointless. So this matrix is a 2 by 2. Matrix B is a 2 by 3. Can we multiply A times B? Yes, because the columns in A match the rows in B. What will the dimensions of my answer or product matrix be? Maddie says 2 by 3. Okay, so I'm going to come up with a 2 by 3 answer matrix. Now, I'm going to write out a little bit more work than I always write out. Sometimes if they're bigger matrices, I write this work out anyway because it can be helpful. You might get lost in a matrix multiplication. So I'm going to write out, once I decide that I can multiply them, I'm going to write out my two matrices right next to each other like I'm multiplying. And then remember, for addition and subtraction, you just add and subtract corresponding entries. Well, we don't have to have the same orders here, so that's not how multiplication works. Okay, multiplication works by multiplying rows in the first matrix by columns in the second matrix. And so I'm going to make a little note to myself. In order to multiply matrices together, I multiply the rows by columns, which that sounds familiar, right? That's the order of a matrix, a row by column. Okay. So what that looks like in matrix multiplication is, in the first matrix, I'm going to pick the first row, which is 2, negative 3. I'm going to multiply it by the first column in the second matrix. Okay. Now, when multiplying those things together, multiply the corresponding entries, like the first entry in the row multiplies with the first entry in the column. The second entry in the row multiplies with the second entry in the column, and then we add those two products together. So I'm going to write out my work for this. Okay, that would be 2 times 1 plus negative 3 times 4. Try to keep it in black. Okay. Whatever that is, 2 times 1 plus negative 3 times 4, 2 plus negative 12, negative 10, that's my first entry in my answer matrix.
Okay.
To get the second entry in my answer matrix, this would be the first row and second column. Then I'm going to take my first row, 2, negative 3, and multiply it by my second column in the second matrix. Okay, so my second entry would be 2 times 0 plus negative 3 times 3. Remember, first entry in the row would multiply by first entry in the column, second entry in the row by second entry in the column. And that would be 0 plus negative 9, so negative 9. First row, second entry. And this is 2 by 3. I still have one more column to go on my first row. How do I get that third column? I take the first row, 2, negative 3, and I multiply it by the third column. So I would have 2 times negative 1 plus 3, negative 3 times 7. Negative 23. Yes, Ethan.
Whose idea was this?
I'm not certain. Then I want to get the second row. So I just repeat the process. If I want the second row, first column entry, multiply the second row by the
Second column.
that would be the second row, second column entry. I want the second column first, second row, first column entry.
So for that second row, first column.
Multiply it by the first column, right? Okay, so now I would go and I would pick up negative 2, 5, and I would multiply it by the column 1, 4. So in the row below, I'm going to have negative 2 times 1 plus 5 times 4. That's negative 2 plus 20, or 18. Does anybody have any questions about where my numbers are coming from? Things that need to be clarified? Okay, so then I continue on, taking my second row times my second column. That would be negative 2 times 0 plus 5 times 3. So 0 plus 15. And then my last entry would be my second row times my third column. So negative 2 times negative 1 plus 5 times 7. That would be 2 plus 35, or 37. Apologize that all my stuff got squished together. But my answer matrix should be the 2 by 3 matrix, first row, negative 10, negative 9, negative 23. second row, 18, 15, 37. Yes, sir.
So if you had a matrix where all of the entries were just like a multiple of 2, could you just like put the 2 on the outside?
Yeah. It'd be like factoring out a greatest common
Yeah.
factor. And then you might, but you might re-multiply it at the end. Like,
Yeah.
we generally don't write them with their,
Yeah.
the scalar on the outside. You would distribute it.
Can you multiply, theoretically, like a 3 by 4 and, oh, it has to be. A 3 by 4 and a 4 by 8?
Sure. Get a 3 by 8 matrix. Yeah. Could be fine.
That sounds.
Now, we can do A times B. Let me ask you this question. Can you do B times A?
No.
No. Because if you did B times A, you'd be doing a 3 by 2 times a 2 by 2? So you're not allowed to do that? You can do that, can't you? Oh, it's 2 by 3. I wrote it wrong. Thank you. Okay, thank you. 2 by 3 and 2 by 2. So we cannot do that. You guys are right. Because the columns in row 1 or in matrix 1 don't match the rows in matrix 2. Okay. So that means that where we normally say multiplication is commutative, 3 times 5 is 5 times 3, that's not true for matrices. Multiplication is not commutative. Okay, it doesn't work both ways. Okay. Okay, could you please try this one on your own?
I'm good at it.
Remember, some things I would do before I get started would be make sure I could multiply them. And if I could multiply them, I often like to think ahead to what order my product matrix will be. That would be helpful for you when you're doing your matrix multiplications. Even check your sentence.
So what should your answer matrix be? This is 1 by 2, this is 2 by 2. What should your answer? This is really I would argue that those things that you have are the things that you have together into one. Because like you'd be the first entries multiplied together, last and the second entry multiplied together. You don't have to worry about the spot. It's the sum of those things.
Okay. I would look at this and say, here is a 1 by 2. This is a 2 by 2. Can I multiply them?
Yes.
Yes, I may. They have columns equal to rows. And so my answer matrix is going to be a 1 by 2. And again, I like to think about that because that would be really helpful to make sure that you're doing the matrix multiplication correctly. And remember, to do matrix multiplication, you multiply rows by columns. So, first row times first column. 3 times 2 is 6 plus -5 times 0. 0. Okay, so that would give me a first entry of 6. I'm going to write that down. 3 times 2 plus negative 5 times 0. To get my second entry, I'm taking my first row times my second column. 3 times 1 is 3 plus negative 5 times negative 4. 20. So that would be 23 for the second entry. And I'm getting that from 3 times 1 plus 5 times, or sorry, negative 5 times negative 4. There's my answer. Any questions? Make sure you practice these tonight. One last example that we want to look at is, of course, a word problem. I know you've been waiting. Here's what I'm going to say about the word problems. You know, matrices are just a way for us to organize things, right? Data. So I would argue that any of the word problems with matrices can most likely be solved lots of different ways. And I would argue a lot of us who would normally read this might not solve it with a matrix. But I'm going to encourage you to think about which matrix operation you could use and then how to set that up. So you have, I could be adding matrices together, I could be subtracting, I could be multiplying by a scalar, or I could be multiplying matrices. Okay, so I would encourage you, try to think about, which matrix operation would be useful here. So this says, the table below shows the number of calories burned by individuals of different body weights while performing different types of exercise for 1 hour time periods. So if I weigh 130 pounds and I play basketball for 1 hour, I will burn 472 calories. Whereas if I weigh 155 pounds and play basketball for 1 hour, I will burn 563. And then it also gives me data for jump roping and weightlifting. Okay. That's just information that's provided. It asks a question then. A 130-pound person and a 155-pound person play basketball for 30 minutes, jump rope for 15, and lift weights for 30. How many calories does each individual burn? Well, think about this. Are you going to be adding some matrices together? No. Okay. How would you normally, if you were just a 130-pound person, you knew that you burned 472 calories playing basketball for 1 hour, but you only play for half an hour? How would you figure your calorie count then?
Divide by 2.
Divide by 2, which is really doing what?
Multiply by 1/2.
Multiplying by 1/2, right? So I think that's the key, is to think about, how would I do that without a matrix? I'd multiply the time I spent by the number of calories I would burn. And so I'm thinking in my head, this is probably going to be a matrix multiplication. So I want you to try to set it up with matrices, even though I know you can solve it without matrices. Okay. So we talked about dividing by 2 or multiplying by 1/2. That means when I say that I was playing basketball for 30 minutes, this is in terms of hours, so we could change 30 minutes to
0.5 hours.
0.5 hours. What could we do for 15 minutes?
0.25 hours.
0.25 or 1/4. And then for lifting weights would be another 0.5 hours. Is everybody okay with that? Make it in terms of my original time. Okay. And then what I would do is I would go back. Do you see how this chart really looks like a matrix? Okay. I'm not going to change anything about it. I'm just going to draw it as if it were a matrix. 472, 590, 177, 563, 704, 211. And this is a 3 by 2 matrix, 3 rows, 2 columns. And we've already kind of decided, if I were trying to figure this out on my own, just for one sport, I would just multiply my time by the number of calories. Okay? So we want to multiply all those things by the times we spend doing them. We have 3 times, basketball, jump rope, and weightlifting. So I could make 2 different matrices. A 1 by 3 or a 3 by 1. Which one should I make? A 1 by 3 or a 3 by 1?
3 by 1.
Why 3 by 1?
Wait, no, never mind.
No, 1 by 3.
Why 1 by 3?
Because then you can place it. Fine.
Then you can multiply. Why?
does the first matrix, and the number of columns in the first matrix equals the number of columns in the.
You need the columns in one to equal the rows in the other, right? If I were to do this 3 by 2 and put it behind, would a 1 by 3 or a 3 by 1 work? No. If I were to put the new matrix in front for multiplication, would a 1 by 3 or a 3 by 1 work? A 1 by 3 would work, right? So I would use the 1 by 3 matrix, and then I would just put them in the order that they come in the columns or in the rows of the other one. I've got basketball, jump rope, weightlifting. So I would start with basketball's 0.5, jump rope is 0.25, and weightlifting is 0.5. And then think about how that's going to work with what you know about matrix multiplication. What's going to be my product matrix order? My answer is going to be what ordered matrix?
1 by 2.
1 by 2. Think about why that would make sense, because then we're going to have a total for the 130-pound person. We're going to have a total for the 155-pound person, which is what we want. And then if you did your matrix multiplication, you'd be doing this first row, 0.5, 0.25, 0.5, times that first column. And the basketball time is going to match with the basketball calories. The jump rope time is going to match with the jump rope calories, and the weightlift time is going to match with the weightlift calories for the 130-pound person. And if they did all three of those activities, then we would add them together. So go ahead and do that real quick in your calculators. Do your little rows. On this one, I probably won't write out all the work. I'll do 0.5 times 472 plus 0.25 times 590 plus 0.5 times 177. So I get the 130-pound person will spend 472 calories.
So the 130-pound person could save quite a bit. Could save 15 minutes by just playing basketball.
I don't remember what that stated.
I got 563. Does that seem right? I think I did something wrong.
Possibly because they literally would have been better off just playing basketball.
No, jump rope. Okay.
Does anybody confirm my numbers? John, you're confirming my numbers? Okay, I thought I did something wrong. I must have did something wrong in my other class. Nobody checked me. Okay. You know, I mean, you could argue that, like, yeah, if I was trying to burn the maximum number of calories, I shouldn't have done that. But, you know, like, if you're working out for an hour and 15 minutes, you might want to mix it up. But it depends on what your goal is, right?
No, perfect sense.
My goals get shredded.
Oh my
I
god.
guess school.
If you,
Just so you know, that's going to be on video.
Is that